Kia ora koutou, nau mai, haere mai. Welcome to lesson 32 for introductory physics. In the previous lesson, we talked about simple harmonic motion, the idea of something oscillating, vibrating back and forwards on the spot. It wasn't traveling through space. Its center of mass, its average position over time was set at one location, and then it would oscillate back and forth, the pendulum swinging like that, a mass on a spring going back and forwards like that. But the center of that motion, the average time position, was not changing. What we're going to look at today is the idea of wave motion, which is when that center position is changing over time. That will lead us into a discussion of sound, setting us up to discuss wave phenomena in the next lesson. And then in the final 3 lessons of this course, we take those concepts and we move into electromagnetic waves, which is light. So this is sort of the beginning of the end for this course. So our goals today are around what I was just saying. We want to define waves. We're also going to talk about a wave pulse because that will help us with some of the phenomena in the next lesson. We want to define the types of waves, so difference between mechanical and non-mechanical, as well as properties of the wave, which includes things like crest, trough, amplitude, wavelength, speed, period, and frequency. We've got transverse and longitudinal as another distinction between types of waves, and then, as I said, we'll introduce sound waves, describe those, talk about how all those wave properties apply to sound waves. And we'll actually mention a little bit about the process of hearing, but just in brief, we're not going to get too much into the biology of that. So these 2 parts to this lesson. First one is just about waves in general. The second one is on applying what we've learned to sound waves. So let's look at waves. If you have something which is vibrating but also traveling at some speed, then we call this a wave. So a wave is something that is oscillating in time while also traveling in space. You'll remember that simple harmonic motion or vibrations were just oscillating in time. So over time, it would oscillate back and forth, but it wasn't traveling through space, whereas for a wave, we do have that traveling. So a wave extends from one place to another. It moves through space. It has some kind of displacement. As I mentioned in that learning outcome slide, we want to define a wave pulse because it can be useful, and we'll talk about it a bit more in the next lesson. We're not really going to deal with it much today, but I just want to define it since we are defining waves in general. So a wave pulse is like the idea of just a single little flick of a rope. If you have a big long rope, you might have done this with a hose or a skipping rope in school. If you flick the end up, you'll see this little wave, this little pulse, this little bump travel along the wave, just like I've illustrated on the slide. That little bump is called a wave pulse. So just keep that in mind. We'll come back to that. If instead of one little flick, you continuously shook the end of the rope up and down, so you just sat there constantly going up and down with the end of the rope, then you would get this wave pattern traveling down the rope. So it's like those little wave pulses, but it's just continuous. It's just heaps of them, one after the other, and you get this wave shape. And this may look quite similar at this point to that graph we saw of simple harmonic motion, and of course that's the point, that similarity there. So a wave can be treated as a series of neighboring pulses. That means that in the next lesson, when we talk about wave pulses a little bit and talk about some of the phenomena we see with them, it means we can also apply those same results to generic waves, full waves, continuous waves like this. So the wave pulses are good for understanding some phenomena and generalizing our results. When we're dealing with a wave, we have to understand the properties of the wave. One of those properties is whether it is a mechanical wave or not. So a mechanical wave is just a wave that involves some kind of matter moving, some kind of medium moving. Remember that mechanical physics, when we talked about mechanics, that was the idea of just stuff moving, matter moving. Same thing here, mechanical waves means we've got matter moving as a result of this wave. So in the previous example, we had rope being shook up and down. The rope was the medium. If you've got water waves, waves on the surface of water, water is the medium. And so we're going to see that all different types of waves, not all, sorry, a lot of types of waves have a medium. If they have a medium, they are a mechanical wave. If they're not a mechanical wave, if they don't have a medium, then they are a different kind of wave. They're non-mechanical is just the general term, but specifically the most important one is electromagnetic waves, which I've hinted at a few times. We've talked about when we talked about light and photons and things, and we'll come back to that in the second half of this section, so the last 3 lessons of the course. Let's go back to our idea of waving a rope. You're shaking it continuously and it's making this series of bumps travel down the rope. If you push pause on it at some instant, then a nice theoretical perfect series of those bumps would look like a sine curve. It would look just like that. It's the wave pulsing up where you've pulsed it up and down where you've shook it down again, and you get this sine wave traveling along the wave, along the rope. So that's if we push pause on it. Remember, when we push play, it's moving along the rope. We'll come back to that. But if we push pause on it and just look at it at a freeze frame snapshot of it, then we can define some terms. We have crests, which are the high points, the peaks, and troughs, which are the low points. So crests and troughs are just those points of maximum displacement. Amplitude is the height of that wave, so that distance, the measurement of that maximum displacement. So remember, in simple harmonic motion, we already talked about this idea of amplitude, the idea from your equilibrium position, how far do you move left or right, right? However far you move, that was the amplitude. Exactly the same idea here. If that rope was a straight line, it would be straight down the middle. But if we instead shake it to get this wave motion, then the distance from where it would have been to the peak, the center point to the peak, is the amplitude of the wave. Wavelength is hopefully self-explanatory. It's the length of the wave, the length from one crest to the next or one trough to the next. You can actually measure the wavelength from any point on the wave to any identical point on the wave. As you can see, I've indicated one partway down the slope of this wave here, but you'll notice that it's not just to when the wave is at that next same point, it's when the wave is next identical, which means it has to be sloping downwards. When it comes back to that same height the first time, it's actually pointing upwards, and so that's not a wavelength. You have to complete the motion one full oscillation, so from where you are all the way to one end, back to the other end, and back to where you started, so that you're now traveling in the same direction and at the same location. So that's the wavelength. For that reason, it's easiest generally to measure the wavelength just from crests or troughs. 2 crests or 2 troughs, get the distance between them. It's just a bit less confusing than defining the wavelength for those other intermediate points. Push play on our wave again, and we get this kind of motion. So this is our wave motion, just a wave traveling along the rope or whatever the medium happens to be. Wave speed is just the speed at which it is traveling. So you just choose any point on that wave. The crests or the troughs are the easiest. Again, for simplicity, we often choose those. And you just measure the speed, the same way you'd measure the speed for anything. What distance does it cover in what time? Your meters per second is your wave speed. So the wave speed is just that, the speed of the crests or the troughs, or again, of any point on the wave. That's all wave speed is. The wave period is a little bit different, and I want you to take the time to think about these different terms for waves, because they are often confusing when we're dealing with different speeds, different times. So when you're calculating the wave speed, you will have measured a time. So I'm going back a slide again. For this wave speed, you do measure a time. You might measure the time it takes for one trough to cross the screen, to go from there all the way across to there, and you might time that, and then you measure it and you figure out the wave speed. The time it takes for that, you need to calculate in order to, you need that time in order to calculate the wave speed. But that's a different time than the wave period. For the wave period, what you're doing is you're choosing one point in space, and you're seeing how long it takes for one, between crests, for one crest to leave. You start when one crest is there, and then you time how long it takes for the next crest to come along, as you can see in this GIF here. I've actually, when I made this GIF, I paused it when it gets to the peak, just so you can see the period, what it gets to, and then it resets. So in reality, that wave is just moving continuously, as we saw. As I said, the difference here is that for the wave period, you choose one spot in space, one position in space that the wave is traveling past, and you time how long between 2 consecutive crests, because that is the period. That's how frequently or how long it takes for one crest to be where the previous one was. The wave speed, You will need to time it if you were going to measure it, but you're now talking about a single crest moving through space and how quickly that does it, what the speed of that crest is. So that's a big tripping point for a lot of students, getting that distinction between timing the wave period, so choose one location in space and time how long between crests, versus determining the wave speed, which is to follow one crest and see how quickly it's moving. Right? Frequency, same idea as we had with SHM. If you know the period, that's how many oscillations there are per second, how many crests are going past per second. How many seconds it takes for one crest to go past to the frequency. Same idea about how many crests are going past per second. And the equation is still exactly the same. F is equal to 1 over t, or t is equal to 1 over f. Units are still hertz. Exactly the same idea as we had with periods for SHM. But we've now got this extra relationship. We've got this idea of a wave speed as well as our frequency and our wavelength and our period. So is there a relationship there? There is. We've got V is equal to F lambda. The wave speed is equal to frequency times the wavelength. That might take a little bit of thinking about to really grasp why that is true. You can trust me that it is true, and you can think about it a bit more if you want. But the way to think about it is that if you remember, the wave speed is how quickly the crest is moving, and the wavelength is how far there is between two crests, and the frequency is how many crests pass a specific point per second. Right? So if you've got a number of crests passing a specific point per second, then that means that if there's lambda distance between them, you must have had some velocity v in order to get that lambda distance occurring at the right frequency, if that all sort of makes sense. Right? So it's a little bit tricky to really grasp the relationship between those conceptually. I do want you to try and do that at the very least, make sure you're happy with all of the definitions for wave speed, frequency, and wavelength. But if you can, try and conceptually grasp that relationship there. As a little double check, because this is a formula that I'm essentially just telling you to believe, you should check the units. V equals F lambda. Lambda is a length, frequency is a frequency, so it's got hertz, which is seconds to the -1. So we have meters per second, which is exactly what we would expect for a wave speed, right, for a speed. We have a medium. We've talked about the idea of a medium for mechanical wave, and the medium is the material which is carrying the wave. So what is the medium actually doing? Right? We already saw that when we looked at the period. If you choose one part of the wave and just follow it up and down as the wave travels past, you'll see that that specific part of the wave is going up and down as per the green dot on this GIF. And that should look hopefully very similar, because it is SHM. It is simple harmonic motion. Every particle in the matter is moving vertically with simple harmonic motion. Now, there is, again, the distinction between our theoretical models and real world physics. If you were to shake a rope as violently as I'm showing in this GIF, so that you had this big amplitude, then this is not going to quite be true, because the rope is actually going to, one part of the rope is actually going to move back and forwards a little bit as it goes up and down, just to facilitate that wave shape. But for a small enough amplitude wave, so if you've got a fairly small amplitude, so you've got a little rope that's just oscillating a little bit as it travels, then it's actually very close to true. With things like waterways, where you've got the surface of the water, obviously water particles are going to be moving. They're always moving in a fluid anyway. But to make a wave, again, if it was as big amplitude as that, then you've got water particles that have to fill up that area of the wave and evacuate the area where there's a trough. They've got to fill up the crest and evacuate the trough, and then the next second they've got to be away, out of the way of the crest, because there's now a trough there, and they've got to fill up where the crest is, where there was a trough before. So you're obviously going to get a lot of motion of water between the crests and the troughs as the wave travels along. Again, if you've got small amplitudes, it's pretty close to being accurate. Something like this is very close to being true. The more violent or more energy you get in that wave, then the less true it becomes. So again, it's an idea of understanding this model. For a lot of cases, we can just use this SHM model, and it works perfectly well within our tolerances. So what is actually moving then? What is moving? If the particles are moving vertically, but the wave is traveling horizontally, there must be something moving. For us to call it a wave, for us to observe this wave motion, this phenomena, what is actually moving? If the particles in the rope are just going up and down, what is it that's going sideways? It is energy. Waves are transporting energy across space, not matter. The oscillation of one part of matter causes the oscillation of the next. It passes on the energy. So this particle goes up, it pulls this one with it, so it gives it the energy, drags it up, it does work on that next particle. And then if gravity pulls it back down, the next particle is pulling the next one up, and so it does work on that, and then gravity pulls it down, and so on. And so all these particles pass the energy along to the next one. So you don't need to worry about it right at that atomic level, as I was just talking about, but you do need to grasp the concept of a wave being a transportation of energy, not matter. Matter stays where it is. As I was just saying, the matter essentially travels vertically in SHM, or it travels on the spot. Somehow it vibrates on the spot. The energy does not stay where it is. The energy is passed along through the medium. That is what a wave is. Another definition is transverse wave. Transverse means across, that's just what the word means. So a transverse wave means that the oscillations are occurring perpendicular to the direction of energy transfer. If the energy is going that way, then a transverse wave will be going up and down, right? Perpendicular. That's what we're talking about with ropes. It's also what happens with water waves. The energy travels across the surface of the water horizontally, and the waves travel vertically, right? The wave motion is vertically. So the wave travels horizontally, the particles of the medium travel vertically. The other type, so that was transverse, where the wave motion is perpendicular to the particle motion is perpendicular to the wave motion. Here we have longitudinal waves, which is where the particles oscillate along the direction of energy transfer, right, or parallel to that direction of energy transfer. This is a bit harder to visualize, but as you'll see soon, it is a very important one. A spring or a slinky is a reasonable example. You can hopefully see from this GIF how the particles, if you watch one of the little coils, you'll see it moves back and forth in that same direction that the energy is traveling, right? It's traveling back and forth along that horizontal line as well, rather than up and down as we saw with the rope. So that's a longitudinal wave. And longitudinal waves are very important because they are, or sound waves are longitudinal waves. Sound waves are one example. So sound waves, if a tree falls in a forest and no one is around to hear it, does it make a sound, right? One of these classic little questions that a lot of people don't really get around to answering. They just hum and ha over it. These are fun because they're sort of language questions more than anything else. Does it make a sound? It depends entirely on who you ask. If you ask a philosopher, then you're going to get a lot of interesting conversation, and you'll probably not really have any better kind of idea afterwards, right? It depends on a lot of different factors. If you ask a filmmaker, they'll probably say yes, but we'll have to add it in post-production or something like that. If you ask a physicist, then the answer is yes. Sound in physics is a mechanical vibration of matter such that energy is transported. There's no umming and ahhing. There's no, how do we define this? How do we define that? Sound is the mechanical vibration of matter such that energy is transported. If a tree falls, there will be mechanical vibration of matter such that energy is transported. Right? It's open and shut for physics. So easy for us. For the other ones, that all comes back to the idea of this language use. How do we define sound? If you define sound as what someone hears, then you need a someone there for there to be a sound, and that's essentially the crux of that question. But for physics, always going to be a sound. As I said, sound is a longitudinal wave. Air is usually the medium. It's the most common one for us anyway. And the air particles bunch up or spread out. So air is a gas. When we're talking about a rope, we're talking about the solid where everything's constrained. The particles are attached to their neighbors. Remember, gas is this big bunch of loose particles that are all just flying around. So again, we make some models, some simplifications. And what we do is we pretend for a moment that all the particles are stationary, and then we think about the oscillations in that sense, keeping in mind that in reality, they're actually flying around. But all the stuff we do, all the physics we talk about, still works even once we let them be flying particles again. What happens is that we get the particles of the medium, the air, oscillating backwards and forwards in the direction of the wave motion. So here we've got a wave that is traveling to the right across that GIF. you'll see if you follow those little red dots, those are just highlighted particles to make it easier to see what they're doing. They are oscillating back and forth. And what we see is we get these sort of clusters of particles, these clusters that are like the peaks, they're called compressions that are traveling along. And in between, we get these rarefactions, which are like the troughs. They're the little, the emptier, less dense portions of the gas. And those are called the rarefactions. And again, they travel along. So we've got a wave motion. It just looks slightly different than what we saw for transverse. And of course, that's quite difficult to sketch. It's very difficult to draw wave motion for a longitudinal sound wave because we've got dots, we've got these little particles, and we've got them moving in the direction of motion, and we're trying to illustrate rarefactions and compressions. Pretty hard to try and sketch. So what you'll see below that is just the standard sine wave. It looks like our wave motion for a rope or whatever material we were talking about, water or ropes. But instead, it's essentially a graph representing the compression of the particles or the density of the air at that point. So you'll see where we've got the compression, we've got all these dots all lined up. That's very dense air. There's more particles there than there are elsewhere. And the rarefactions, where the particles are more spread out, there's less dense. So you could think of that as a measure of particle compression or as a measure of the local density at that location. And that looks just like a regular wave and travels just like a regular wave. But you've got to remember, even if you draw it like that and think about it in terms of that density or anything else, that it is going to be actually made up of all these little particles moving back and forth, as we're seeing in that top part of the GIF. The other way you can think about it is, rather than density, you could think about it as pressure, where there's more particles bunched up in that compression. Remember, compression and pressure are very similar terms. There's very similar ideas behind them. Where you've got all that compression of particles, you're going to get a higher pressure because you've got more particles, more collisions. So you could also do it as a graph of pressure, which is essentially the same thing as a graph of compression. Sound wave can travel through other mediums. That's how tin can phones work. If you've ever made one of those kinds of little phones when you're a kid and you talk through them, the sound wave is traveling along the string rather than the air. The sound wave that you create when you speak into the can is air, and the air vibrates, but the air is inside the can, causes the can to vibrate, which causes the string to vibrate, which causes the can at the other end to vibrate, causing the air inside the can at the other end to vibrate, and then the person can hear it. So sound wave can travel through other medium. Remember that a sound wave in physics is simply the mechanical motion of matter such that energy is transported through space. So it doesn't matter if it's air, if it's a gas, or if it's a solid or a liquid. Sound is just that mechanical vibration transporting energy through. There are lots of different ways to make sound. Most of them involve, or they all involve vibrating matter, but most of them involve different ways to cause air to vibrate. That's the most common, because that's how we, as I said, we generally hear everything through air coming towards us. Things like musical instruments, we've got pianos, guitars, and violins. They all use strings to vibrate the air. Strings vibrate, they move the air around them as the strings vibrate, and that causes the air around them to propagate those sound waves, to transport energy through space, and then you can hear it. For a brass instrument, the lips of the brass player are vibrating at one end of the metal tube that is the brass instrument. Those vibrations travel through the tube, amplifying and coming out the other end as a big sound wave. And when you speak, your vocal cords are vibrating inside your throat, and that is causing the air in your throat to vibrate and come out, amplify out through your throat and mouth, and cause the sound wave in the air. So they're all about different ways we can oscillate the air particles and cause that sound wave. The frequency of the sound wave that you create is going to be the same as the frequency of the thing that's oscillating. Remember that we've got the idea of simple harmonic motion as just something vibrating on the spot. If we have something vibrating on the spot, it's going to cause the air next to it to vibrate at that same frequency, and that will cause a sound wave at that same frequency. So we have sound waves being the same frequency as the thing that's vibrating to cause them. And that makes perfect sense, because if you've got something that's pushing this way and then swinging back and then pushing this way again, every time it pushes, that's extra pressure, that's going to cause a compression, and you're going to get this compression, and then another one next time there's after one more period. So that means the frequency of both has to be the same. Otherwise, you'd end up with the motion of the thing vibrating, trying to cause a compression, but actually being a rarefaction. It wouldn't make any sense, right? It doesn't make physical sense. So the frequency is always going to be the same between the thing that's vibrating and the sound wave in the ear that leaves. And that's exactly how speakers work. Speakers have a little cone designed to sort of catch a bunch of air, because it's a cone, so it's full of air and it pushes it, and it uses magnets and stuff. We're not worried about that side of it, but it uses magnets to cause the cone to vibrate back and forward rapidly, and that causes the air to vibrate at that same frequency. So by controlling the cone, they are controlling the air, which controls the sound wave. So just to go back to a GIF similar to that one we saw before, imagine that grey line on the left is our speaker. So now we're looking at the creation of the sound wave. That grey line is the speaker. As it pushes forwards into the ear, it bunches up the particles. It increases the pressure, which is a compression, right? So we get that compression, which is like the peak of our wave, the peak of our density graph, if you were going to do it as a density graph. And that peak travels along, it travels through space. And then as the speaker pulls back, so the grey line moves back to the left, then it's sort of making this this extra space, and so the gas, the air has to spread out to fill up that space. So that causes a rarefaction, a lower density area, because the gas is spread out. And then it pushes back again and causes another compression, and so on. So that's all a speaker is actually doing, or anything that creates a sound is actually doing. At the other end of that is us hearing it. So objects make a sound wave, it travels through the ear as the propagation of energy through space, right? Just the energy being transported from particle to particle through collision. And at the other end of that is our ears. If we didn't have the ears to hear the sound waves would be irrelevant. So how do sound waves work in our ears? Our ear is basically catching the sound wave. We have a big ear, external ear, to try and catch as much of the sound wave as we can, and it sort of funnels it in to our ear canal. The sound wave travels through the ear canal, and at the end of the ear canal is the eardrum. The eardrum is a little elastic sheet, and it basically oscillates with the sound wave. So exactly the same as the idea of the sound wave being caused by something oscillating next to the ear. The same thing happens if you have air oscillating next to something. So at the other end of that, when the compression hits the eardrum, remember, compression means higher pressure, higher density, more air particles for an instant. And that means you're going to have more pressure on this side of the eardrum than you do inside the head, and the eardrum pushes in slightly. Then the next moment you've got a rarefaction, so the eardrum pulls out slightly, and then another compression pushes it back in. And so the eardrum oscillates with that same frequency, and that's what we hear. Right? The eardrum is actually transferring it to little bones, which interact with the cochlea, which turns the motion of the eardrum into little electrical signals, and they go to via the auditory nerve to your brain. But that's getting into biology. I don't expect you to worry about all of that. Again, fascinating stuff, as a lot of these processes that we sort of brush up against are, but we're more concerned with the motion of the wave itself rather than specifically how the biology of hearing works. And so that is how hearing works on a very superficial sense. Since our eardrum is doing the vibrating, and the eardrum is vibrating at the same frequency as the sound wave, for the same reason as I talked about the thing vibrating to cause the sound wave has to be the same frequency as that sound wave in ear, the frequency of your eardrum vibrations has to be the same as that of the sound wave in ear, because it's being caused by those compressions and rarefactions. That means the frequency is the only thing we're actually hearing. We're not hearing the wavelength, we're hearing the frequency. The wavelength tells us how quickly or how spread out those wave crests and troughs are in space, but we're standing at one point. All we hear is how frequently those crests hit us. So if those waves were traveling a bit quicker, they would hit us more frequently, but we're hearing the difference in frequency, not the difference in wavelength. It's a bit of a technical little distinction, but it is important to just be aware of that. That said, if we know the speed of sound, then we can calculate the wavelength based on the frequency we hear. And indeed, we often have questions and calculations along those lines. For a little bit of terminology again, coming back to language, the sound frequency and the sound pitch are actually kind of the same thing in a lot of everyday language, the pitch of a sound or the frequency of a sound. In physics, they are slightly different. The frequency is the frequency of the wave itself, how frequently those crests pass a specific point. The pitch is the impression we get of a sound's frequency. So the sound has a frequency. When it hits our eardrum and turns into a signal which gets sent to our brain, that signal interpretation in our brain, that is the pitch. So the pitch is something that we experience. The frequency is a property of the wave. So it's a little distinction. It's not that critical, but I just thought I'd point that out. Humans can generally hear anything in the range of 20 hertz to 20 kilohertz. That's a huge range. It's a very impressive ability, our ability to hear sounds through that range. 20 hertz. So that's 20 oscillations a second, right up to 20,000 oscillations per second. That's how sensitive our eardrums are to all these different sounds, these different frequencies. So it's a really impressive feat of biological construction. And it's like there's nothing else that has that bigger range. We're talking from 20 up to 20,000. That's 20,000 times or 1,000 times as big, right? 20 up to 20,000. So it's a huge range of different sound frequencies. So very good range there. The downside is that that's hard to maintain, and as you age, you tend to lose some of those frequencies, especially the higher ones. Is just the systems have to be very precise and fine details in order to hear that big range of sounds, and that makes it easy to damage and easy to lose over time. Obviously, you don't want to hear drastic sounds that can cause damage. It is easy to damage. If a sound is below our hearing range, so less than 20 hertz, then we call it infrasonic or infrasound. Infrasonic, infra meaning below, so below sound is basically saying it's below what we can hear. The alternative, the opposite side of that, ultrasonic, above, ultra being above, ultrasonic is above 20,000 hertz, so above our hearing range, also called ultrasound. Do be aware of the distinction between ultrasound as the category of all sound waves above 20,000 hertz versus ultrasound as the medical imaging process, right? They have the same name, they are distinct, but ultrasound, the medical imaging process, does use ultrasonic sound, ultrasound, in its imaging process, which is why it got that name. So to recap sound waves are longitudinal waves. So the air particles are vibrating in the same direction as the wave motion. Waves traveling this way, the air particles are going to be oscillating in that direction as well, parallel to that. They consist of compressions and rarefactions, which are like high pressure and low pressure, or high density and low density, or just bunched up and spread out, however you want to think of them. Sound waves are mechanical waves, therefore they require a medium. So it doesn't matter if the sound wave is traveling through a block of concrete, through air, or through water, the sound wave part will look the same, right? Though you will still get those compressions and those rarefactions within the particles. In something like a block of some kind of solid, those compressions and rarefactions won't be quite as dramatic as in the airwaves, because obviously they're still limited by where they can go within their space, within their little solid bound. Remember, they're bonded to all their neighbors in the solid, so they've got that bounded limit where they can travel. So you'll still get the limits within its location in the solid, but you'll get a bunch that all sort of move to the right and together and then move back to the left. So you still get this idea of compression and rarefaction. It's just not quite as dramatic as we can see with air. We already met some properties of waves. We need to think about how they work for sound waves, and they are hopefully fairly self-explanatory. Wavelength is still the distance between two peaks, but now the peaks are compressions for longitudinal waves. So we have the wavelength as the distance between two compressions or rarefactions. Frequency, same idea, number of compressions or rarefactions that pass a point every second. Period, again, 1 over the frequency, same relationship, and it's just the time between two consecutive compressions or two consecutive rarefactions. The wave speed, how quickly those compressions or rarefactions travel through the medium. So all of those are exactly the same as we saw before, but now thinking about longitudinal sound waves. Amplitude in a longitudinal wave, that is a bit harder to understand. How do we talk about amplitude? Because in a transverse wave, it was easy. Here's your straight rope that's not being shaken. When you do shake it, it goes up this far and down that far. That's the amplitude, right? That was pretty straightforward for a transverse wave. How do we do it with a longitudinal wave? The essential idea, we're not actually going to define it. We're not going to measure it in the same way as we can with a transverse wave. Transverse waves, I expect you to be able to calculate and do measurements based on amplitudes of waves. I don't expect you to for a longitudinal wave. I expect you to understand what it is though. And that is the difference between how compressed and spread out those compressions and rarefactions are compared to if there was no wave there. So compared to just your default density everywhere. So how big is that change in density or change in compression how spread out they get as a result of the wave. So hopefully to illustrate this, if you had no particles, no wave, then the particles would be evenly spread out as per that top image there. The next one is just small amplitude wave. You get this slight distinction, but it's kind of hard to pick up. But there is a compression and a rarefaction in that wave there. So you can see just above the S and just above the above the lit of amplitude, you've got these compressions, and in between them you've got these rarefactions where they're just slightly spread out. But it's not super obvious. It is there, but it's not really clear. So that's a low amplitude wave. A high amplitude wave is going to have a big difference in density between the compressions and the rarefactions. So you can see we get these really obvious compressions, these big clusters of particles, and then very few in between where they're spread out. That is a large amplitude wave. So that is the difference in amplitude for a longitudinal wave, which includes sound waves. What does that mean in terms of the sounds we hear? Sound wave amplitude is the volume of the wave. The more energy the wave carries, remember a wave is just the transport of energy, the more energy the wave carries, the more difference there is between the compression and rarefaction, then the more your eardrum will vibrate in response. Remember that the higher compression means higher pressure. Higher pressure means your eardrum is going to bend more, it's going to move more in towards your head because your internal head pressure is the same. That's just atmospheric pressure inside your head. But if the pressure on the outside of the eardrum is higher, the eardrum will move further inwards. It will stretch more, and it will cause those little bones and all of that processing to be increased in magnitude. And then the rarefaction is a lot lower pressure, so your eardrum will move out a lot more. So it's basically, it causes your eardrum to vibrate with a greater amplitude, which causes the sound to be louder, to appear louder. And of course, if the sound gets too loud, then that eardrum is simply stretched beyond its elastic limit, it ruptures, and it causes damage and potentially permanent hearing loss, which is why you don't want to subject yourself to overly loud sounds. It's a very real danger. The idea of prolonged loud sound that's not enough to damage, to rupture your eardrum, but is enough to provide lasting hearing damage, that's the same idea. It's just that you're stretching that to its very limit. So it hasn't ruptured, but you're getting right up towards that limit, and it both damages the eardrum itself, but also all the components on the other side that are measuring that magnitude of oscillation. So very easy to damage, as I said, very fine components, that huge range of hearing frequencies, huge range, impressive, fine little components, very delicate system, and so loud sounds are damaging. How does a sound wave travel? So we've already sort of talked about this, but I just want to talk about it a little bit more. How does sound wave travel through a medium? In a rope, we saw each particle pulls up the next one, pulls up the next one, pulls up the next one, passes that energy along, and that's how the energy is transported. But how does that work in sound? Remember that the air particles are all colliding, they're all flying around the room, and as they collide, they pass energy. We've already met this idea of a collision causing energy transfer. We saw it with heat. Right? And we just saw it in general with collisions, but we get the same thing with sound. So with a sound wave, what you're getting is that compression where a whole bunch of particles bunch up, they all collide more frequently with all of their neighbors, and then they might, because they collide, on average they're traveling back a little bit, and there's not as many particles there, so they travel a bit further without any collision, so they're not sending any energy back the other way, and then the new wave of particles comes along, collides with all of them, and gives them some more energy to keep them going that way. So it's sort of just this flow, this constant flow of collisions moving that energy along through space, and that's all it really is. Remember, of course, that air particles are constantly flying around in all the directions, so there's actually energy going every direction constantly in air, in just any gas. What the sound wave is doing is it just means that there's a few more collisions transporting energy in the direction of the sound wave. So there's still the collisions going in every direction in reality. As I said, it's not actually a whole bunch of particles that aren't really moving and just oscillate back and forth. They're flying everywhere. The sound wave just means there's a few more collisions transporting energy in the direction of the sound wave. That's all a sound wave really is. How quickly do those collisions occur? Do they transport that energy through? It depends on a lot of things. The standard speed of sound that we'll refer to is 343 meters a second, or just 340 if you're only worried about 2SF. That's for 20 degrees Celsius air at 1 atmosphere of pressure. And because the sound wave speed is essentially how quickly those collisions are transporting that energy, you can imagine, or you can hopefully understand how that energy rate, that transfer rate, that speed of sound would be different for different conditions. If there was wind is overall motion of all the particles. That means they're already heading in one direction. If the sound wave is traveling in that same direction, then the sound wave will travel a bit quicker because all the particles are being carried along a bit quicker, which means the energy they have is being carried with them. And so they get that little boost of speed from the wind. Or if they were traveling against the wind, the opposite thing happens. And the energy is trying to go that way through all the collisions, but the particles are being pulled this way because that's what wind is. Wind is just the motion of the particles. So that would be a bit slower. As we said, temperature is the speed of the average speed of the particles. It's the translational kinetic energy. If the particles have a bit more energy, then they can move over and collide with the next one a little bit quicker than if it was colder. And so the hotter the air, the hotter the gas that's transporting the sound, the quicker that sound will travel, because that collision will happen a little bit quicker, which means that energy gets passed along a little bit quicker and the sound wave moves a bit quicker. So in temperature, around about a 1 degree Celsius increase in temperature relates to around about a 0.6 meter per second speed increase. So it does actually, it's a noticeable speed increase. And humidity, the more water vapor equals faster. Water vapor, nice big particles, lots of mass, therefore lots of kinetic energy, means they can carry lots of energy with them. And so that energy travels quite rapidly along. As I said, though, sound doesn't just happen in air. Sound is the mechanical transportation of energy through any medium. And so that means that there's different speeds of sounds in any medium based on how quickly they can transport that energy through collisions through themselves. In air, as I said, we have around about 340 meters per second. In water, it's around 1,480 meters per second. So it's 1.5 kilometers every second. For air, it's 1/3 of a kilometer every second, which is still useful. But for water, it's 1.5 kilometers a second. Still useful. I don't know why I said useful. It's still very quick, 340 meters a second. For water, though, 1.5 kilometers a second. For iron, it's 5,000 kilometers, 5,000 meters, 5 kilometers a second. For diamond, 12 kilometers a second. 12 kilometers in 1 second. That's how quickly that energy is transported through. That's because diamond is a very rigid, solid, very perfect crystal structure. And that means that any disturbance in one particle, one atom, is very quickly passed on to its neighbors. And that means the sound wave travels very quickly. We only ever hear sound in air, though. Even if a sound wave travels through another medium on the way to us, we only ever hear it from air, because at some point that vibrating object, but that has sound in it, whether it's a diamond or whether it's a steel train track, as per one of the worksheet questions, excuse me, or whatever it happens to be that's doing carrying that sound wave, at some point the vibrations of the particles that are carrying that sound wave in that object will cause the air around it to vibrate. And that is what we hear, the propagation of that sound wave through air from the vibrating object. So even if we're underwater, there's usually some air left at the end of our ear canals. Water doesn't normally go all the way in the ear canal right up to the eardrum. At least not normally. You could force it to, but it doesn't normally do that. And that means that even a sound wave traveling through the water all the way up your ear canal at some point is going to be passed on to air for the last bit of the journey, and your eardrum will be oscillating with the air in your eardrum, right? Air in ear. So that generally we always hear sound from air particles. And that's the end of the lesson. Quite a bit to hopefully grasp. We've got what waves are, a whole bunch of properties, and how that relates to sound waves. Do go back, make sure you're happy with all of those terms. As I said, the distinction between determining wave speed and period or frequency is a common tripping point. Being able to really be confident. I know one of the assignment questions relates to that as well. So do make sure you get some practice, get some thinking done around that wave speed versus period, what we're measuring, what times are involved for each of those. But there is overall quite a lot of terminology to learn in this lesson. I know a lot of our lessons are more conceptual, less to memorize. In this one, there are a lot of terms to remember. So do take the time to just do whatever you need to do, flashcards or just writing lists, repeating those terms. Do make sure you are happy with all of those terms.